Hello, this is Smoke Point by Arbitrary. It is a puzzle including pointing thermometers. So let us look at the rules of this puzzle. So, normal Sudoku rules apply. Put the digits 1 to 9 in every row, every column, and every 3x3 box. Crop key dots, digits separated by white dots are consecutive. So if this was a 1, this would have to be a 2. It could be in any order, so something like this would work. I would assume that not all dots are given, so it's possible for, let's say, these two to be consecutive, these two to be consecutive. Next. Pointer thermals. Digits along thermometers must increase in value from the bulb end. So digits like this must increase in some capacity. It doesn't have to increase by 1, it can increase by any amount as long as the next digit is greater than the previous one. Additionally, the thermometer tips point towards a cell containing the digit within the bulb. So let's say this is a 1, 2, 3, 4. Then this cell, the tip points in the direction which must then contain the digit in the bulb. So somewhere here will contain a 1. The value in the tip indicates the distance of the digit between the tip and this cell. So this is a 4, that means the 1 that it's pointing at must be 4 cells away, which would be here. There may be other instances of the digit between the tip and this cell, so it's possible for this to be a 1 as well. So it doesn't block line of sight, you can see as long as it's 1 4 cells away. Additionally, there may be, if a thermometer has more than one tip, so like this, then each tip points toward a different instance of the bulb digit. So you could have something like 1, 2, 3, and then 4, 5. So this 3 would point in this direction, and this 5 would point in this direction. Something like that. Yeah, okay. So, with that, let us begin solving. This puzzle is actually going to be a bit trickier than the one that we did before. This is a moderately more difficult one. I do think we start with the longest ones first though, although they may not be true. Because these longest ones have to be at least 4. And in fact they do point at each other, which is very interesting. So this thing points at a total of 6 possible squares, and therefore can be anywhere from 4 to 6. This also points at 6 squares. So this is anywhere from 4 to 6. I think there are many problems with this being a 6 though. Because if this pointed at the thermometer itself, it is basically forcing whatever cell this is to be somewhere on the thermometer. So this cell would then be somewhere on the thermometer if this pointed at the thermometer. What does that mean? Yes, that fails because if this cell is here, then this must be, well, by this thermometer, this must already be quite large. Oh, but it is possible, isn't it? It could be... Yeah, there is one case in which it would work. A 1, 2, 3 here, forcing a 3 there, causing a 4, 5, and then 6 here, which then, you know, points at this cell. And this could be a 4, which points here, which could then be a 1. So this is very, very barely possible. It is possible for this to be 4, 5, or 6, I think. Could it point to this cell? I mean, could it point to this cell? It can't actually, yes, because what we did there, to make sure this works, what do we need to do? We need to make sure, because this is here, we're basically drawing our thermometer extending from this cell. And so we have to make this as small as possible and make this as large as possible to give us enough space between the two thermometers. So yeah, we can see it like joining these two thermometers together. We get like a very long looking 6 cell thermometer. So this must be as large as possible, and this must be as small as possible. And in fact, we already saw the only way to do that is if this was exactly 1, 2, 3, 4, 5, 6. Now it's even worse actually if this happened, because what this does is if this was the orange cell, not only are you making this bigger because you are pushing it further down the thermometer, you're also making this smaller because this is now a 5 instead of a 6. So you are basically forcing that to be a lot more digits between this cell and this cell, which definitely is not possible. You can't have 1, 2, 3, 4 and then a 4 here, because then there's nothing between 4 and 5. So it is definitely not pointing at this cell, which means that this is not a 5. And because this is diagonally symmetrical, I believe we can do the same logic with this, where this cell is definitely, if this cell was a 5 or a 6, then this cell is seen by one of those cells. So this is not a 5 either. Yeah, I didn't say a lot of things, did I? My mic was off the entire time, but I hope you got what that means. Okay, I'll run through the entire piece of logic all over again because my mic was off. I'll probably edit this part out so that you guys can seamless transitioning, but I'm keeping the timer because yeah, okay. So let's go through the logic. This cell sees one of these cells because we know this is at least a 4 and at most a 6. Now what cells can it see? What if it was a 5 or 6? It would then see the thermometer. Now we know this is also a 4, 5, 6 by diagonal symmetry. It sees one of these cells. Now if this cell saw, we can therefore say that somewhat one of these cells is then linked to here, which means you can form sort of a kind of a, like if you pressed this cell into here, if they form the same cell, you sort of form this like long-ish thermometer, which is only made possible if it's exactly 1, 2, 3, 4, 5, 6 or something like that. Now notice that if this cell was in this cell, then you'd have a 7 long, which doesn't work because this can't be at least a 7. So these two cells cannot exactly be the same, which means that if this pointed at the thermometer, it would have to be from this cell, in which case that cell would be the third one from the start, like so, and could be made possible with a 1, 2, 3, 4, 5, 6 sort of deal, which then points here. This cell is therefore also a 3, which is made possible if this is a 1 and a 2. So that is possible if this points at one of those cells. However, we know it does not point at this cell because we proved that if it did, the resulting quote-unquote thermometer would become too long. So this can't be a 5, but it could be a 4 or a 6. If it was a 6, we saw that the only way to complete it is if this was a 3, because we have a 6 long thermometer, this cell which has to be exactly a 3, and the 3 would then be here. Otherwise, if this was a 4, then by this thermometer alone, this 4 would have to go 4, 3, 2, 1. So this would either be a 1 or a 3, putting a 1 here or a 3 there. And I can place orange here for our possible options. And by diagonal symmetry, because these two thermometers are exactly the same, just mirrored across the diagonal axis here, we can therefore say that this is also a 4-6 pair, which looks into one of those cells, and is also equal to that cell. So this is also either a 1 or a 3, this is a 1, or this is a 3. Now, this looks pretty interesting, because these can't both be 3s, because then you have a 3 there, right? If this was a 3, 3 is here, forcing that to be a non-3. So that sort of means that if this is a 3, then this is not 3. But also, if this is a 1, because this is not a 1, this is not a 1 either. So this forms some sort of pseudo 1-3 pair where it's one of them is a 1 and one of them is a 3. And then similarly, one of them is a 6 and one of them is a 4. I'm not exactly sure how that helps, because it may or may not be a bit more complicated than that. But this is what I can see so far. Now I wonder what else I should look at. These thermometers are pretty far away from the edges they point at, which is unfortunate. Like this one's 5 away. And it has to be at least 3, so I guess we can put 3, 4 or 5 in there. But this cell could be anything from a 3 to 6, right? So it could even be pointing at this cell. I guess we could sort of slowly but surely limit values here. So yeah, this is at least a 3 and at most a 6, because it only points up to 6 cells. Could it be a 3? Yes, it could. It could be a 3, 2, 1, and then a 1 goes there, which is fine. Could it be a 4? 4 goes here. Now that's really interesting, because this cell is equal to this cell. But if this was a 4, then by this thermal alone, this would have to be at most a 2, which fails this cell, because this cell can't be a 2 or a 1. You don't have enough digits to place here. So this can't be a 4. It could be a 5 pointing at this cell, because you could make this like a 2 or a 3. Which then makes this a 2 or a 3, and then this would be like a 1 or something. Although, wait, okay. Can I say that one of these cells is a 1? Can I say that? We know because, yes, either orange is a 1. Because we know this is a pseudo 1-3 pair, either the orange is a 1, or the blue is a 1, in which case 1 is placed here. So one of these cells is definitely a 1, and one of these cells is definitely a 3 by equivalent logic. Same here, one of this is a 1 and one of these is a 3. So I can therefore say that 1 does not appear on this bulb. If this was therefore a 5, which points here, this therefore has to be a 3 then, which would then put 2 there, which can actually happen because you could have 5, 3, 2 or something. But 5 is, it appears to be possible, and 6 is probably possible, because yeah, 6 is probably possible. I think this is fairly similar in design to this one specifically. Yeah, I mean it does look somewhat similar, I think, because we know this is at least a 3. Oh, in fact there's at least a 4, because we know this isn't a 1, so minimally this is a 4, which means that it's pointing somewhere in this box. Now this 4 could point there, but that doesn't work because a 4 would force this to be a 2, right? 4, 3, 2. But none of these cells are a 2, so this can't be a 4. It's either a 5 or a 6, which means it either points here or there. Now what if it points there? Well, this is through 2 or 3, right? Which has to be here. But this can't be a 3 by these. We know there's a 3 here. So this can't be a 3, it must be a 2. Which makes this a 1, which I think is possible. Wait, no, because, yeah, that fails, right? A 5 here fails. That's really tricky. But a 5 here implies that it is looking at this square. So we're going to remove that color. And this square is the same as that cell as a result. Now, if this was a 5, what could this be? Well, it can't be a 1, but it can be a 2 or a 3, implying that this is either a 2 or a 3. But by this cell, we know that 3 exists in one of these cells. Either blue is 3, or orange is 3, which forces 3 here. So one of these is a 3, which removes 3 as an option. That is therefore a 2, which forces a 1. But that also fails, because one of these is a 1? Yeah, no, that's not true. Because it could be 3, 4, 5, 6. Oh. Okay, well I guess I'm wrong then, because yeah, I thought this would be a 3, 1. Why did I think that? I did not think that. Okay, so I guess in fact 5 is possible. Well, that's something. Which means it either points to this cell or that cell. Okay. Let's look at the other thermals then. What are these? These look pretty interesting. This cell sees one of 5 objects, so it's either 3, 4, or 5 objects. I mean cells. Could it be a 4? Then those cells are the same, which I think is plausible. I guess I should mark that one of these are 3s. One of these are 3s. One of these are 1s and one of these are 1s. I suppose that's somewhat helpful. So this is it could be a 1, it could be anything up to 3. So this is what it sort of looks like. Which means that this can't be a 3, right? Because 3 points at 3 points there. Oh. 3 points there. Which means that's fine. And then 4 points there. And then 5 points there. So this cell is in one of those cells, definitely. Which I guess somewhat restricts where it goes in this box. But it could be any of these cells, there's no restriction there. This one might be even worse because this could be at least a 3. It's 1, 2, 3 like that. But it could be anywhere 2, 4, up to 7. Wow. It could be anywhere up to 7. So anywhere from 3 to 7. Which are those cells specifically. Anything we can do to restrict that? I'm not sure. Actually, yeah, can we say something about what this cell is? If this is at most a 5, then this would be at most a 3, but it can't be a 3, so it's either only a 1 or a 2. So this can this in fact be a 5? No, because a 5 looks at this cell, but this cell can't be 1 or 2. It can't be 1 clearly, because there's nothing below that, but it can't be 2 either, because that forces a 1 here. We didn't know one of these are 1s, so that fails. So it can't be pointing at this either. So this is not a 5. The issue is it could be 3 though, that's really annoying. Okay, what could this cell be? Could it be a 4? Could it be a 4, 5, 6? It could, but it can't be a 1 because of those. So it's a 2, 3 or 4, right? Which forms something similar to that. Which makes me think I might be looking for a pair maybe? Not sure exactly. I mean, if we figured out that's a 3, then it would be like 1, 2, 3, right? In fact, because this can only be maximally a 5, how does that affect things? Like this clump seems pretty interesting. Like, I don't think I can fit that many different numbers on there. Like if this is a 3, there'll be a 1, 2, 3, right? But this could even be a 1, 2, 3 as well. That wouldn't clash. Huh. Well, this is definitely a start. I mean, this can't be a 3 because of these, but it could be a 2 or a 4. If this was a 5, it would point at that and say 2 or 4. Well, we don't actually know it's a 5 or a 6, so this could be a 6. This could be pointing at that, and then this could be 3. So that's something. Can I say this is 3, 4, or 5? I guess so, I guess so. Or we know this can't be, like, can't be much either. It's either 3 or 6. It's either this or that. Yeah, okay, I really don't see what there is. I mean, I guess, okay, because we know this is a pseudo 4-6 pair, we can say that this isn't a 4. But that again doesn't really help us because there's not anything that is pointing to anything else. It's not being pointed at either. Is it? No, it's not. But okay, I guess that's something. Oh, it's the same thing here. This is a pseudo 4-6 pair, which means that whatever this is, it's always a 3. It's never a 6. Because 6 is either there or there, which sees that cell always. So that's not a 6, that's a 3. Which fixes that. It forces that to be a 2-1. So 3 cells away, or 1 is being seen. Oh, that's our first digit. Well, those are our first digits, in fact, because that's a lot of digits. So this can't be a 1, which means that's a 1, because we know 1's in one of these cells. So 1 is actually the orange section, which is 2, 3, 4. So this is 3, 4, 5, 6. So that clears up a bunch of stuff. I'm going to remove the color a bit. I think that helps, because we no longer need the color anymore. But this now can't be 3 because 3 cells away you can't put a 1 there, so this can't be 3. This can't be 4 because you can't put a 1 there. Wrong digit. So a 1 is in one of those cells, and a 1 is in one of those cells. Now let's see, if this was a 5 then this would be a 2. I think that's fine. Okay. This is anywhere from 2, 3 to 4, or it's either 2 or 4. But I don't think that matters much. I mean, what is this? This is at least a 3. It can be up to 7. But it can't be 3 because of this. It can't be 4 because you can't put a 1 here. There is already a 1 there. It can't be 5 because of that. So it's either a 6 or a 7. So it's one of those cells that it's looking at. Which isn't too much of a problem because you could put a pretty small number in here. This is 6, 5. Or I could put anything from up to 4. Oh! Yes! Wow! And this 1, 2, 3 sees that cell. So because minimally this is a 4, it can't be a 5, it can't be a 6 either because this isn't 2 more than 6 at all. So this must just be a 4. Which means that one of those cells is a 4, but since this 4 sees that, that's a 4, which means that this number must be a 7 because it's 7 away. Oh, wow. Okay. So it's a 5 or a 6. This 4 means that's a 2. That we don't know yet, but we therefore know that... not sure. We know that's no longer a 4. That is not a 4 either. Because of that. It forms a 2-3 pair, which is very useful. Okay. So 3 goes in one of those cells. Okay, I feel like we do still need to use a lot of these that we haven't actually touched yet. We've touched every thermometer except these 2. Those seem pretty helpless, pretty useless right now. Because this again could be anywhere from 3 to 7. I mean, it can't be 6. So let's see what this is. This is at least a 3. And we'll remove digits along the way. It can't be 4. It can be 3 if it pointed at this cell. It can be 5 if it pointed at that cell. Wait. Sorry, no, sorry, wrong placement. I was talking about this cell. So this is at least a 3 and up to 7. It can't be 4. It can be 3 if it pointed at this cell. It can be a 5 if it pointed at this cell. It can't be 6 because it would then point at this cell, placing a 4 in there. So it can't be 6. It can be 7 if it pointed at that cell. So, but it can't be a 3 because a 3 forces a 3, 2, 1 here, which removes all candidates here. So this can't be 3. And it's either a 5 or a 7. Which are those cells. Pretty tempting to put a 1 in here, but I know that's not true because whatever 1 is, this cell could see the opposite 1. So it may not be a 1 here. Okay, can I put 1 in this box? Yeah, I can. 1 goes there in that box. What about here? 1 is in one of those cells, which sees that. this sees those, so 1 goes there. Oh, so it is in fact 1 in that cell. So wherever 1 is here, the this digit will tell us where. Oh, but wait. Oh, interesting. Look at this. This points to one of these ones, and this points to one of these ones, right? Because they're both 1s. But they must point to the same one, because they can't point to different ones. It's there's only one 1 in the row. So these two point to the same ones, and therefore, it's either this, in which case you have 5, 7, or it's this, in which case it's a 3, 5. So that means one of these cells must be a 5. So they can't be 7, 3, because then they'll be looking at, I don't know, this cell and that cell being a 1, which doesn't work. Okay. That's useful. What about 4? These 4 see those cells. These we already deduced can't be a 4. So 4 goes there. 4 is in one of those cells. 4. I don't know about that. 4 is in one of those cells. And therefore up here we don't know. Okay. What 3 is? 3 is in one of those cells. 3 here. Oh wow. 3 here, one of those cells. 3, I don't know. Okay, we don't know. What about 2s? I don't think we have a lot of 2s yet. Yeah, 2's in one of those cells, but I think that's it. What about here? I mean, 2 can be anywhere. Okay. This is a 5, this is a 2, 3. Definitely. Otherwise, it can't be 6 then. Because if it's a 6, it points to this cell. But since this is a 2 or 3, that means this cell must be a 2 or 3, which it can't be because there's already those in the box. So it has to be a 5, which sees a 2 here, making that 3. That 5, that 2 sees that 3. So this is a 5, that's a 7, which means 1 is all the way here. 3 is now forced into that cell. 1 here is now forced into that cell. And so 3 is in one of those cells, I guess. Not very helpful. Wow, okay. What do we not have here? We have 7, 2, 7, 8, 9. 7, 8s, and 9s are gonna be pretty tough to clear up. Oh, well, I guess, okay, these 7 see those cells. Sorry, those cells. That's not a 7. So, oh, in fact, because this is a 1, we can say that this points at the 4th cell away, so that's a 4. And I guess this 5 also says that's a 4. These 7s point at those cells. So 7 goes in one of there. 7 can be next to 6 or 8, and I'm not sure if we can resolve that yet, because we can't prove anything. Okay. What about 4s? No, 4's in one of those cells. Again, nothing. Right, 5 can't be in there. 5 could be anywhere else. 2 in this box. This 2, this 2, and this 2. See those cells? So that's a 2. So in this box, 2 goes in one of those cells, which forms a 2, 3 pair. These cells are 6, 8, 9. These are 5, 6, 8, or 9. This can be a 6. I guess one of these are 5s, because none of these are 5s. Which see those cells, which means that one of these are 5s. This cell sees that, so that's a 5. So these 2 cells means that's a 5. Okay, well, one of these are 5s. That's on the thermometer, which might be interesting. What can this be? Again, this can be at least... This is... Oh, Oh wow, whoa, look at this. 1, 2, 3, and 4 all see those. So 5 can't be here, because this can't be less than 5. So 5 is just there, which means that this, we know, is at most a 7. So this must be a 7, pushing a 6 in the middle. So this 7 sees that, pushing a 5 there, pushing a 3 there. Making, well, this is not a 6, so that's a 6. This is 8, 9. How are we gonna resolve the 8s and 9s? Oh, I guess it's this consecutive section. Yes, because this 7 must now be next to an 8 because it can't be next to a 6. So this is a 7, 8 pair. So that's no longer an 8, that's a 9, that's an 8. These cells are 6 and 9, nice. These cells are 2, 3, 8. 3 can't be in both of those cells, so that's a 3, that's a 2. The 2 mean, this 2 means this is an 8, that's a 2. Wow. I think we've used every... Yeah, we've used every clue at this point, so it's just normal Sudoku right now. So 4 goes in one of those cells. I don't see anything else. No, nothing there. Well, those cells are 6, 8, 9. This cell is a 5, 6, or 9, but it can't be a 6. It's a 5 or 9. Yeah, 4 is one of those cells, so that's not a 4. Meaning 4 is there. These are 5, 7, 9. These can't be 5, so 5 is here. Meaning that's a 6, meaning that's a 9. That's a 6. 6. So those are not 6. These are 7, 8, 9, I think. Those are 6, 7, 8, or 9. Which are the same here. So those are also 6, 7, 8, 9. 7 sees those. So I guess 7 is one of those cells. Okay. So this is 8 or 9, we know that from the column. We know a 2 must be there. What? This is 4, 6. Where's 6 go? 6 can't be there or there, so this forms a... Oh yeah, and 6 can't be there either, so 6 is there. 4 is there. This is a 7, 9 pair, which means that this is an 8. That is no longer 8. These two are... Oh, that is an issue. Wait a minute. Where does 6 go in the box? Doesn't 6 have to go there? Oh yeah, this 9 means that's an 8. Wait, why did I say this is an 8, 9? Oh, because I didn't realize this 9 resolved there, so that's a 6. Okay. So in this row, it's still true that 6 can't be in those cells, 6 can't be there, so that's a 6, that's a 4. This is a 7, 9 pair, which is true. So this is a 5, 8 pair, which is true. This 5 sees that, so that's an 8, that is a 5. That is no longer 8. That scared me a lot, because I keep making these stupid mistakes. That's an 8. That's a 6. This 8 means that's a 9, that's an 8. This 9 means that's a 7, that's a 9. These cells are 7 and 9 as well. These cells are 7 and 8. These cells are 6 and 9, which we can resolve with that. So 9 here, 6 there. This is 2, 7, 9. These are... Oh, this 9 means that's no longer 9. What if I put a 0? This is this must have a 3. That 3 sees that, so 3 goes there. This is a 7, 8, or 9, which means that forms a 7, 8, 9 triple. So that's no longer 7, no longer 7 or 9. That's a 2. That's a 7. That is a 9. That is not a 9, I guess. This is this 7 sees that, so that's an 8. That's a 7. That's an 8. That's a 9. 4 must go there. That is definitely a 2. This 8 sees it that, so that's a 7. That's an 8. The 7 sees that, so that's a 9. That is a 7. Oh, we have this as well. So this 7 sees that. So that's a 9 and that's a 7. Solved. Oh, wow, this was in fact quite hard. Yeah, I really enjoyed this one actually. The breakthrough was pretty interesting. I especially like the initial logic regarding these guys. Yeah, that was pretty neat. And then forming these two, which look at this cell, yeah, that was pretty neat as well. I really enjoyed that. Alright, well I hope you enjoyed it too. I will see you. Bye bye.